Hi everyone, welcome to AI Crack channel. This is Akash Gangwar and today we'll be studying continuity lecture 1. So let's get started. This is QOD 16, take the screenshot. So let's get started with the basics of continuity at a point. In limits chapter we have studied about LHL and RHL. So basically let's say this is a function. Let's say this is a function and we are talking about this point A. Then just at the right side of A is RHL and on the left side we have LHL. Right? So this was our discussion in limits. Now, when we are talking about continuity at a point, we mean that at this particular point, f of a would be equals to LHL equals to RHL. If this condition is being satisfied, in that case, we can say that the function is continuous at that particular point. So basically what is happening, we have a function over here. Now, in that function, we have a point A. We are looking at the left-hand limit. We are looking at the right-hand limit. And if left-hand limit equals to right-hand limit equals to some finite value, obviously, and that is also equals to f of a. In that case, we can say that the function is continuous. Now let's take few examples. So let's say we have a function like this. So this is our point. This is our point A. Now we know that f of a, let's say f of a is being defined over here. Let's say this is value, some value b. So f of a is being defined over here. F of a equals to b. Although the limits goes to infinity, but f of a equals to b. This is how it is being defined. In this case, LHL doesn't exist. LHL equals to RHL, not equals to LHL and RHL. They both don't exist, right? Now in this case, we can say that the function is not continuous because these are not existing. So these should exist, should be a finite value, and also should be equals to the function value at that point. So in that case, we can say that the function is continuous. Now let's discuss few important discussions and conclusions based on the discussions and concepts we had. So the first one is, let's say we have a function fx. If fx is continuous at a, in that case, this implies that limit x approaches a, fx exists, right? If function is continuous at a, that means limit x approaches a, fx is existing. But the vice versa is not true. Why? Because let's take an example. Suppose we have a function like this, and we are talking about this point. We have an open circle over here, and function is defined at this point. Now we can say that these limits are existing. They're not infinity. They're not going to infinity. They are actually existing. They have a finite value over here, both LHL and RHL, right? But in this case, the function is not continuous. Why? Because the function is defined being over here, and here we have an open circle. So function is not continuous, but limit is existing. So vice versa is not true. But if a function is continuous, then in that case limit exists because that is a basic part of a function being continuous. Now the second point is, if fx is continuous at a, in that case we can say that f of a exists, right? Because that is also a part of the definition of function being continuous. But reverse is also not true. Here as well it's not true, here as well it's not true. So let's take one more example. Let's take the same example once again. So we have an open circle over here, and function is being defined over here, but limits are existing. So in this case, function A is existing, f of A is existing, but the function is not continuous. So these are the two important pointers and conclusions based on the discussion we had. Now an interesting point about continuity is it is always talked in the domain of function. What does that mean? Let's say we have a function 1 upon x. Let's say we have a function like this. So we know that x is not defined at 0. So basically x cannot be 0. If you're talking about the domain, then x belongs to r minus 0. This is the domain. So unless given in the question, if we are asked if this function is continuous or not, we'll say this function is continuous because we'll assume that they are asking in the domain of the function. But if they are deliberately asking that, okay, tell us the continuity, discuss the continuity of this function at x equals to 0, in that case we can definitely say that this is not continuous at x equals to 0. So whenever in any question, in any examination, in any question, if domain is not given, if they haven't deliberately asked you to discuss the continuity at a particular point, then we should be discussing the continuity at only those points which are defined. So basically 0 is not defined over here, so we'll not be discussing the continuity at 0. Got the point? So this discussion leads us to another concept of point functions. So basically point functions are always continuous. Why? Because they are being defined at just one singular point. Now what is the definition of continuity? We say that f of a, let's say this is point A, this is f of a equals to b. F of a equals to LHL equals to RHL in that vicinity. But over here, the function is not being defined at any place. It's being defined at singular point. That is a. That is just one point. It's not being defined at a plus h or a minus h. So we cannot calculate the limits over there. So since we cannot calculate the limits, these are not possible to calculate. Only this is being defined. So this automatically becomes continuous. In the layman terms, we say that a function is continuous when we don't have to lift the pen. So basically we are going on and on and on. So this function is continuous, this curve is continuous basically. But if we have to lift our pen at some point, maybe this, like this or this, so in that case we can say that the function is discontinuous. Over here we are not lifting a pen, although it's just a point, so we are not actually lifting a pen. So that's why it's also continuous. You can get the intuition like this also, but the mathematical reason is this only. So related to this concept, let's discuss left continuous and right continuous. What does that mean? Let's say a function is like this only. Let's take one more example over here. So it's being defined in this range, a to b. Now this is actually c and this is actually d, f of b. Now the function is being defined only in this range. So domain belongs to a to b only, right? So now if we are talking about a point a minus h over here, that is not in the domain, so we don't have to calculate LHL over here. So this function is actually left continuous, and this function is right continuous, right? So this is how we have to define it. We're not defining left hand limit over here, we're not defining right hand limit over here, and that is how the nomenclature works. Now let's talk about inverse of continuous functions and discontinuous functions. So basically, inverse of both continuous and discontinuous functions is also continuous and discontinuous respectively. Let's look at it graphically. Let's say we have a function like this. Now we know that when we are talking about inverse functions, graphically, it means that it is a mirror image. The inverse function is the mirror image of the actual function about y equals to x line. This is y equals to x line. This is 45 degree, right? This is 0 comma 0. So this is the mirror image. So basically if this function is continuous, then this function automatically becomes continuous and discontinuous. Let's say we have an open point over here, then we'll get an open point over here as well. So in that case it becomes discontinuous over here, right? So this is the graphical representation of continuous and discontinuous functions, uh, discontinuous inverse functions. Now, since we have talked a lot of theory and we know that the continuity is more or less about limits only, we have to eventually calculate the limits only. So let's look at the illustrations, and this is the kind of questions which we are going to get in the examination. We'll see a few examples which have actually come in the examination. Now this says that fx equals to this when x equals to not, x not equals to 0, and b when x equals to 0. So basically the function has to be continuous. So LHL should be RHL should be b basically at x equals to 0, at x equals to 0. So basically we are calculating limit at around x equals to 0, and that should be equals to b. Now we can clearly see that this is a kind of standard limit format, right? Cosec ax divided by ln of 1 plus x square. Now I would prefer writing cosec ax as 1 by sin ax. So I would write it as e raised power x minus 1 whole cube divided by ln of 1 plus x square into 1 upon sine ax. Now to make this as a standard limit, what I would do, I would multiply and divide by ax. So this becomes my standard limit. Now to make this as a standard limit, I would have to multiply divide by x cube, right? So let's do that. That would become e raised power x minus 1 divided by x whole cube, and we have x cube over here, divided by ln of 1 plus x square into ax divided by sine ax, and we have an additional ax over here. So this gets cancelled. This becomes x square. Now this also becomes a standard limit, right? This is standard limit, this is standard limit, and this is also standard limit. So now what we have got over here, this is 1 multiplied by, this is also 1, and this is also 1, or and divide by a basically. So we have got 1 by a as the answer. So basically b should be 1 by a for this function to be continuous. We had the space over here. I congested over here. Now let's look at one more example. Let fx equals to log of 1 plus x raised to power 1 plus x minus x divided by x square. Then find the value of f of 0 so that the function is continuous at x equals to 0. So basically, we have been given a function and we have to find the value of f of 0. Eventually, we have to calculate the limit. Now we know that f of 0 cannot be found out directly because this becomes 0 minus 0 divided by 0. So basically, this is 0 by 0 format. So eventually, we'll have to calculate the limits. And those limiting values should also be equal to f of 0 so that the function is continuous, right? Now let's calculate the limit. So we have limit x approaches 0 log of 1 plus x raised to power 1 plus x minus x divided by x square. Now using the log property, I would take 1 plus x over here. So it becomes 1 plus x log of 1 plus x minus x divided by x square. Now I can use the expansion ln of 1 plus x, right? So that would give me 1 plus x. So that would become x minus x square by 2 plus x cube by 3 and so on, minus x divided by x square. Now let's try to simplify it further. So basically I can see that I'll get x minus x square by 2 plus x cube by 3 over here. So x minus x square by 2 plus x cube by 3 and so on over here. And also plus x times x minus x square by 2 plus x cube by 3 and so on minus x divided by x square. I forgot to mention one point that even in the question we have been given log of 1 plus x. We assume that this is log of base to e. So basically you have to assume that this is nothing but ln 1 plus x. So whenever you see a log of 1 plus x in limits or continuity equations or derivability equations, you have to assume that this is nothing but ln of 1 plus x, right? So that you can use the expansion accordingly. So now you can see that this x cancels out this one. So this cancels out this one. And we have got minus x square by 2 over here and plus x square over here. The other terms are actually higher order terms. So we know that when x is approaching 0, we can neglect the higher order terms. So that would make all these terms as 0, right? So this becomes 1 by 2 as the answer. Limit x approaches 0. So basically f of 0 should be 1 by 2 for this function to be continuous because we got to find the limit as 1 by 2. Now let's look at the real example which has come in PGDBA 2017. So we have been given this as the function. This is a fairly simple question as compared to the ones which we have seen in examples. Now let's try to solve this one. So basically our critical points are -1 and 1. So we see that the function is changing at only -1 and 1 only 1. So that's why we have to check at these points. At other points, these are the polynomial functions and we know that polynomial functions are continuous. So for every x greater than 1, this function is continuous. For every x in this range, this function is continuous. And also for every x less than -1, this function is continuous. The only turning points are -1 and 1. So we will be checking at those points. So let's talk about -1 point. So this is our first point. First point, x equals to -1. Now we'll calculate limit, left hand limit and right hand limit, and also the function at -1. So we have to calculate these three values. So for LHL, so basically this is our number line. This is -1. For LHL, we have to look at this side, and for RHL, we have to look at that side. Now for LHL, we'll have to look at this function because this is at the left side. So basically that would be 2 times -1 -1. So that would give me -3 as the answer. And talking about RHL, for RHL, I'll have to look at this function because that is on the right side. So that would give me -1 square plus 1. So that would be 2. So we can see that LHL is not equals to RHL at x equals to -1. So at x equals to -1, this function is not continuous. Now let's talk about x equals to 1. So second point is x equals to 1. We'll do the same process over here, f of 1. So for again same thing. This is point 1. For left hand side, we'll look at this side, and for our right hand side, we'll look at this side. So for left hand side, I'll be taking this as the function because this is in the range. So we have 1 square plus 1, that is 2. And for right hand side, we'll be looking at this function for obvious reasons. So that is again 1 plus 1, 2. And f of 1. So equality is over here. So I'll be looking at 1 square plus 1. So that is also 2. So we can see that the function is continuous at x equals to 1. So the answer should be the function is continuous everywhere except x equals to -1. So this example was fairly simple as compared to the ones which we have seen over here. So these are very typical examples, but these are not very typical. These are very straightforward examples. Now let's talk about continuity in open and closed interval. So we all know that, let's say this is interval a comma b, and this is interval b, a to b. Now, when we are discussing continuity in open and closed interval, we know that this is the definition of open interval and this is the definition of closed interval. Now let's talk about open interval. So we have been given a function. This is open over here. This is a. This is b. For this function to be continuous in this entire interval, it has to be continuous at every point over here. This is x1, x2, x3, all those points, x4, x5. So this has to be continuous in every point, at every point in this entire interval. But we don't really have to care for the endpoints because those are not the part of the domain. Those are not being defined over here. But when we are talking about a closed interval, this is a, this is b, and we have a closed circle over here. Now this becomes mandatory. That function has to be continuous in the open interval, right? On both the sides. Let's say we are talking about a point C over here. So we'll look at the limit LHL, we'll look at the limit RHL, and we'll look at the value f of C. And we have to do this for all these points in the interval, open interval A to B. Along with that, we have to calculate the left hand continuity over here. We have to check right hand continuity over here, because over here left hand side is not being defined. Over here right hand side is not being defined. So at point A, we have to look at the left hand continuity. At point B, we have to look at the right hand continuity, right? To check whether this function is continuous at A and B or not, right? So continuity lecture 1 was still here only, and we'll be starting tomorrow with the continuity lecture 2. I hope you are enjoying the series for calculus, and let's meet tomorrow for the second lecture. Thanks for watching.